So let's do problem 2. So let's look at the following piece of titanium being formed in a standard forming test by Alpha Laval. So titanium, so I know my Young's modulus is equal to 100 GPa. My nu is equal to 0.3. So let's go ahead and let's start defining those values. I've already quit my kernel and cleared all my variables. So let's say that y is equal to 100 times 10 to the 9. That my nu is equal to 0.3. So let's go ahead. Oops, did I clear that value? Oh, I did not clear. So let's quit our kernel. Always good to double check. Quit our kernel, run our notebook, and now we're good to go. So we're deforming this piece of material in the standard forming test. So the gauge factor for the standard reach from there is 2. So F is equal to 2. The gauge resistances are 150 kiloohm, and the shunt resistor is this. When I close the switch, my oscilloscope will read 15 millivolts. So let's go ahead and start to write these down. So my gauge resistance, R1, is going to be equal to 150 times 10 to the 3. My shunt resistors, RS, is going to be equal to 300 times 10 to the 3. All right. So when I close the switch, my oscilloscope will read 15 millivolts. So we need to look at our equivalent strain equation. So EQ. So that's going to be that absolute value of minus 1 divided by F times R1 divided by R1 plus RS. We could confirm this with our expression, and our F is equal to 2. Make sure that's the case. So our F is equal to 2. Let's go ahead and confirm that. Let's press that output, and there we go. Let's just make sure that is the case. So we're going to go all the way back to our lecture 9. Let's look at our expressions here. We have let's go down to our calibration. We don't want that equation. We do, in fact, actually want this equation here that's coming up. So this, so it's our gauge over RS. So you can kind of see that right here. So we've got our equivalent strain. So when we measure that value, we see 15 millivolts. So again, that 15 millivolts leads us to this equivalent strain. But after applying the stress state, seeing the figure below, our oscilloscope will read. So our total strain, which equals epsilon 1 minus epsilon 2 minus epsilon 3 plus epsilon 4, that is going to equal, so our total strain is also equal to our strain equivalent times 5 divided by 15 times 10 to the 3. So that's a huge strain. So our total strain equals 5 divided by 15 times 10 to the minus 3. Minus 3. This times our, so let's put it out on the front, EQ. And there we go. That's quite a large strain value, but again, not completely unbeknownst. So these forming applications start at room temperature, but then the temperature increased to 150 Kelvin, or excuse me, Celsius. So the change, the delta T, was 150 minus 25 degrees C. So, and the same thing for or degree Kelvin. So my delta T is equal to 150 minus 25. Excellent. The strain in the 1,1, so my strain in the 1,1 is equal to 17 microstrain, 17 times 10 to the minus 6. My strain in the 2,2 is equal to 80 times 10 to the minus 6. But I know that this is the strain in the 1,1, so that's going to be negative because I'm compressing. And then here it's also going to be negative as well because I'm compressing that material. So it depends though. We'll kind of look at those values. But anyways, so let's go ahead and write that out. So my strain in the 1,1 equals basically 17 times 10 to the minus 6. My 822 is equal to minus 80 times 10 to the minus 6. So we've got that. And then now we are asked, what's the linear thermal expansion coefficient of titanium? Include the units. What is the rotation to get to maximum principal stress state in this problem? Maximum value of shear stress. Write out the full stress tensor for the original principal and maximum shear stress state. Ooh, good question. So let's look at this problem. We have our coordinate system. We found our material. So what are our stresses that exist here? Well, we have a compressive stress in the 1, 1. We have a compressive stress in the 2, 2. And then the rest of these are 0, 0, 0, 0, 0. So already no shear stresses. So we are in the principal stress state. So that's going to be 0 degrees. To get to maximum value of shear stress, that's going to be 45 degrees. Again, rotation. We need to write out the full stress tensor for the original. So we'll get that once we get the value. That's also the principal. And we'll figure out the maximum shear stress a little bit later on. So we had to figure out what is our linear thermal expansion coefficient. So we know that the strain gauge 2 is measuring, strain gauge 2 equals my strain in the 1, 1 direction plus my thermal strain. My strain in the 3 is going to be equal to my strain in the 2, 2, 2, 2 plus my thermal strain. So I know that my strain, let's go ahead and write that down. So again, my strain in the 3, let's start strain in the 2 is going to be equal to E11 plus ET. And then we'll say that ET is equal to alpha times delta T. There we go. So ET here, E3 is equal to E22 plus ET. There we go. Let's just make sure that that's all correct. Yeah, we're looking good. And we also know that E1, this is going to be 0. This is going to be 0. So let's go ahead and solve for the rest of our unknowns. So actually, let me get this a little bit over here. So I know I could solve for my total strain, which I know. Let me set that equal to my minus E2 minus E3, and then solve for my alpha. And we get a negative value. And what are the units here? So total strain is unitless. So alpha is what? So what are going to be the units of my alpha? My linear thermal expansion coefficient. So what is alpha? My thermal strain is equal to alpha divided by delta T. So it is essentially my change in length over my original length times that delta T. So if we look back all the way, let's go back into our notes, and let's look at alpha. Alpha is going to be essentially, again, change in length divided by the original length. So essentially it's going to be my strain. So if we look at this, it's going to be my strain over K. So it's the change in length, so meter over meter divided by essentially per K. So the change in length per K. So those are the units essentially that we're going to be working with there. So, or K or C in this instance. But that's my alpha. So if that's my alpha, let's go ahead and set that equal. So my alpha is equal to this. So if alpha equals this here. So now I know what my E2 is, or my E11. I can actually now solve because again we got the thermal expansion coefficient, excellent. We got the rotations. Now we need the stress tensor. So now I could go ahead and solve that E11, set that equal to 1 over y times my sig11 minus nu times sig22, and then I could also solve here that my strain in the 2, 2, set it equal to 1 divided by y times sig22 minus nu times sig11. And that's it. So sig11, sig22, and then that's it. As we expected, there are negative stresses. We're good to go. That's it. So that's my sigma 1, that's my sigma 2, 2. Now the only thing we have to have left is my basically my shear stress value. So we're going to have to figure out, okay, so we have one stress value 0, and you saw like this is basically minus 4 kilopascals, minus 9 kilopascals, 9 kPa, minus 4 actually megapascals, MPa. So our maximum shear stress is just going to be this. This again, this value divided by 2. That's going to be this is going to be my maximum shear stress value. That's it. And the center of the circle will also be here. So that's it. That's this entire problem. So let's go ahead and set up our notebook for the next one. Let me quit my kernel here. And we will get into question 3 in just a little bit. So that's it for this problem. So next question, can't stop bending. So let's go ahead and tackle this problem next time. All right, I'll see you next video. Thanks.